In this video, we're going to learn how to do a linear regression in R. Now, I'm going to dive straight into the book at section 7.1.3 here, and I really want you to take a look at the chapter before this section and make sure you can do everything that I need you to do and understand as well what's going on. I deliberately haven't given you code for things like reading in the data. I'm trying to make you a bit more independent when it comes to your coding. So you might hate me for that by not giving you the code. That's fine. I can handle that. But I really want you to start building up some muscle memory for things like reading, calculating columns, and again getting yourself to the point where you can either visualize the data or start performing some statistical tests. So we're going to jump in straight at 7.1.3 here, and we're going to talk about linearizing data. Now I've given a good description of why we need to apply a logarithmic transformation here. I'm not going to go over that again in the video. We're going to dive straight in and we're going to start writing some code. I've already started a new project and a script file, and I've made a comment here. I'm not going to show you the code. I've already got the code above for reading the data, calculating a survival column, and calculating a log survival column. So I'm kind of ready to do something here with this data. Let me show you what the data looks like, just so you can make sure you've got the same results. Initially, the data had these first three columns. You should see the same if you're using the example dataset in the book. And then I've calculated a survival column, which is a percentage relative to a control dosed starting number. I think it was 300. Okay, so that was when there was actually no hydrogen peroxide at all. And then I've linearized this column. So I've applied the log10 function to this column survival to get a new column called log survival. So you should be able to get this far. If you haven't got this far yet, go back, read the book, make sure you can get there. I am going to start by visualizing this data, and to do that I am going to cut and paste what is in the book. I'm going to be very, very lazy today, and I'm going to talk you through this without typing a single character, I hope. So I've got my yeast data frame. I've just shown that to you, and I'm going to take the column for my dose and my log survival, and I'm going to filter both of those columns by the strain. So initially I'm going to use this plot function to generate my scatter plot, and I'm only going to plot the data points associated with the wild type strain. So that's what these square brackets are doing here and here on those columns. I'm just making a conditional statement that says I only want values where the strain type is equal to WT. Okay. Then I'm going to plot. Let's just plot it, see what it looks like. There you go. Let me make that a bit bigger. So you can see that this is a pretty good linear relationship, we think. So I could definitely fit a straight line to that using an ANOVA. We'll do that in a second. That was for my wild type. I'm going to use a second function called points for my 3KO. That's my mutant strain data. And again, I've done the same thing here in my points function as I did in my plot, but I filtered it according to 3KO. And that's all I've done. The only different thing I've done here is I've used different PCH arguments here. The 16 I know is going to give me this solid black. The 1 is going to give me an open circle. And I can show you by running this, Control and Enter. There you go. There's my mutant strain there. It needs a legend, so that's what this line 41 is doing here. Let's run that, and there you go. There's my my key for my legend. I've got axis labels. I've been careful to make sure I've correctly labeled my y-axis, especially because I'm looking at the log survival, not the survival. Okay, and I've given exquisite detail on why I'm applying that logarithmic transformation in the text. So go and take a look. Okay, so at this point, I am ready to say, well, okay, I've got a linear relationship in this data. Let's apply a linear regression And that will allow us to do two things. One, for us to determine whether there is definitely a linear relationship for this data set, and then to predict any value for dose in the range. And actually what we're going to do it the other way around. So I want to know the dose at a survival of 50%. That's my lethal dose at 50%. So we're going to calculate that. How do we do a linear regression for the wild type? Right. So I'm going to create a new variable called, I'm going to call it LM underscore WT. Call it what you like, but basically I'm creating a linear model for my wild type strain. The function to perform a linear regression, a native linear regression in R, is, surprise, surprise, something very simple, LM. It's a function, so I'm going to open up a bracket. I'm now going to feed in a formula, and I want to model the relationship between my log survival, okay, not my survival, my log survival, and I'm going to put a little tilde in there, my dose, okay. I also need to throw in the data, so comma, data equals, and of course it's the yeast data frame we've been working with, right? But I only want the data in that data frame that corresponds to the wild type, okay. So I'm going to open up my square brackets because I'm going to subset this, and I'm going to call yeast data again, and I'm going to specifically look at my strain type column, and I'm going to put a double equals quotation mark WT, okay, and I'm going to, this is the important bit. Now, unlike what we've done for the graphs above, where we've only been filtering the column for dose and survival, I am actually filtering the entire data frame now, so I need to put a comma there and leave that bit blank. So that essentially tells me that I want all of these rows, but I also want all of the columns as well, okay. And then I'm going to do Control and Enter after closing the square bracket and the second parenthesis there. Okay, there we go. There's my data. Sorry, there's my model. It's already popped up. And to look at that linear regression, I'm going to use the summary function LM underscore WT and throw in my model, Control and Enter. Make sure I comment that. And let's take a look at my console output here. I've got my calls. This is what I've made. This is the call I've made. I've got my residuals here. Okay, that's potentially useful. I'm not terribly interested right now. The important stuff is here, this coefficients table. I've got my intercept, and you'll see my intercept for the wild type is about 1.98158. Remember, these are logged values. So if I want to get back to percentages, I need to reverse that log. I've done log 10, log base 10. So I would have to do 10 to the power 1.98. If you do 10 to the power 1.981583 on your calculator, you're going to get a value, surprise, surprise, close to 100. Because remember, at the zero dose here, we had a starting colony count of 100%, right? And everything is relative to that 100%. Okay, I've got a p-value for that intercept, which means that it's very significant. It would be very unlikely that it wasn't about 100% on the left-hand side here. I've also got my this one that says dose. This actually refers to the slope of the fit here, and you can see it's a straight line curve. So this is, if it was y equals mx plus c, this is your m value. You can see it's negative, which is right. And this will give you the size of the slope. So using this value, which I've highlighted here, and your intercept, you could, in theory, calculate any other value along this line. If it wasn't a dot, if I wanted something in between, or if I wanted to actually get a value for the dose from the log survival, I can rearrange it. I can do that. You can see I've got a p-value for my dose, which is also very, very significant. Last things to point out here, I've got a residual standard error, which is very small. That's good, okay? And remember, that's logged. So if I want the actual percentage standard error of the residuals, I would need to do 10 to the power of that. It's still pretty small. It's going to be maybe 4 or 5%, which is pretty good. And I've got a multiple R squared value of 0.9929, and that's ridiculous. It's ridiculously high. It's great. Okay, if you ever get a data set and it's a true data set and you get that value, well done. That's fantastic. It's slightly disingenuous here because I've made this data up. Okay, I wanted it to be linear, so surprise, surprise, it is absolutely linear. Okay, what this R squared value tells you, remember, it tells you the percent of variation of the log survival that is dependent on the dose. So you've almost got 100. You can see you've got a model that's telling you it's 100% related to the dose. That's what your R squared is telling you. And again, an overall F statistic and a p-value which is ridiculously low. Okay, that's kind of what we're expecting here. Right. So my last thing to do here. Well, first I'm actually going to do something useful. I'm going to put my line of best fit on here, so I can use a function called AB line, and I can just throw in my model here, which is really useful, this function, and control and enter, and it will just put my line of best fit through there, just like you do on Excel. In fact, it's a bit better than Excel because it tends to extrapolate kind of just beyond the range without extending your graph. So it looks a bit tidier to me. And then what I need to do now is calculate my LD50 values. So for wild type. Okay, so I need to use my equation of my straight line that's come out of the fit here. And I'm actually going to extract those coefficients for the intercept and the gradient. So let me do that in two new variables before I calculate. How do I do that? I am going to create a variable called intercept wild type. Okay, and I'm going to call my model that I've created, and to get this value, this intercept value, let me give myself a bit more space here. I need to actually put a $sign in, and you can see I get all of think of this as like a data frame for my model. I've got all of these columns here. I want the coefficients, and I actually want the first value in that coefficients table, which is my intercept. Okay, I want to do the same for my slope or gradient, call it what you want. Oops, coefficients 2. So I need to run that. I don't think I ran the first one. Let me just make sure. No, I didn't. There you go. I've now got both of those coefficients in variables that I can use in the calculation. Right, so now I want to calculate my LD50 for the wild type. So I'm going to create a new variable called LD50 underscore wild type. Oops, wild type. And I want to assign to that this calculation. Now, I'm rearranging here. So I am trying to solve for X. So X is the dose. I want to get the dose out at a survival of 50%. However, I have used a log transformation. Don't forget that. So I need to, instead of doing 50%, I need to do log 10 to 50. Whoops. Which is about 1.7 on my graph, right? And then that's kind of your Y value. To get the X value, I then need to subtract the intercept coefficient. I need to divide by the slope. Okay, if I run that, let's print it out as well. There it is. Here you go, I get a value of 5.916. Let's just take a look. So that's going to be about here. Okay, so you're going to do that for the wild type if you can, and then you're going to do the same for this mutant strain here, the 3KO. And the formative and summative task this week for this part of the workshop is to calculate the difference in your LD50s for both of these strains. Okay, so you need to repeat that for the 3KO. Before I finish here, just to show you a bit of visualization annotation here. I often want to visualize values like that I've calculated on my graph. So I'm going to add another AB line. Let's add my LD50 for WT. And I just want that to be a vertical line on the graph. And I'm going to use AB line, but I'm going to use it in a slightly different way this time. I'm going to specify my vertical value. And I'm going to throw in my LD50 for the wild type. I want it to be a dotted line, so line type equals 2. I know that will be a dotted line, and I'm going to make it red. Okay, run that. There you go. I get a nice line there. Now I could annotate this. Yeah, go on, let's do that as well. Let's annotate LD50 for the wild type. So I can add any text to this graph that I want. And I would do it by using, surprise, surprise, a text function. Okay, and I want the first two arguments that your text function is going to take for your graph is the X and Y position of your label. So it's not like Excel, you can't just drag and drop. You're going to put in your X and Y value. Now I want it to appear here roughly. So I'm actually going to put in the X and the Y values for my label. So my X is going to be the dose, LD50 WT, and I want to put log 10 of 50 for my Y value. And then I want to put a label in. And I use my labels argument to do that. And I can't remember what I've done in the book, but I'm just going to call this LD50 WT. Now I could use something like a paste function here to format a string that contains the actual value as well, or I could probably leave it in the figure caption as well. It's entirely up to you. I'm going to just do col equals. I'm going to make sure it's red as well, so it's consistent with my line type. Let's run that. Okay, and there you go. And annoyingly, it kind of does it right through the middle of the line. If you want it kind of off to the side, you can experiment with this pos variable as well. I think pos4 puts it over to the right. Let's take a look. There you go. You'll have to run the graph again. So you'll notice that anytime you want to update a chart, you'll have to run everything again. Okay. Plot. There we go. So I will run this line and this line again. There you go. It's kind of put it over to the edge there. I've forgotten my AB line for the best fit as well. There you go. That's a bit better. I could probably spend a lot of time jazzing that up. I will let you fiddle around with that. It's just a nice aside here. So you can manipulate these visualizations to annotate them as well. Right, that's the end of this video. I've blathered on enough. So good luck trying to get your 3KO LD50 out and then calculate the difference in the doses of those two things for your test this week.